All right, so here I am looking at limits at infinity, part 1 of Paul's notes, practice problems. So limits at infinity. As you can see, we're looking at functions in this first problem here, a polynomial of degree 7, and we're thinking about the behavior of the function as you input ever larger or ever smaller numbers. And what do I mean by that? Numbers that get closer and closer to positive infinity and numbers that get closer and closer to negative infinity. Now, how would I evaluate this limit? The limit as x approaches negative infinity of that 7th degree polynomial right there. I would think to myself, okay, well, these two terms here, the cubic term and the constant term, are going to be overpowered by this 7th power term when I keep on putting in numbers that are bigger and bigger and bigger, whether they're positive or negative or negative. So I only need to concentrate on that very first term. Now, what happens when I raise a negative number to the power of 7? I get a negative number back. This is true if you raise a negative number to any odd power. And so this number here, 4x to the 7, as I make x closer and closer to negative infinity, this is going to get closer and closer to negative infinity itself. And so that's its limit. On the other hand, if I were to make x closer and closer to positive infinity, then this would get closer and closer to positive infinity. And once again, it would overpower the cubic term and the constant term. And so there's the answer to that one, positive infinity. But we must check. Everything must be checked. All right, so their technique is to divide everything through by x to the 7. And then or rather to factor out x to the 7, then using fact 1, we can assert that that will just simply turn into 4. So what is fact 1? If r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r is equal to 0. Right, so yes, I mean, of course I believe these things, right? But anyway. Right. So what's the limit as t approaches negative infinity of h of t? So I think it's this term here which is most relevant, the negative 2t squared. When I square negative infinity, when I square it, I get infinity. So I think it's going to be negative infinity. I'm not sure how much of a justification they really want here, because like in the previous question, it's just sort of using facts handed down from above rather than rigorous argumentations. So I don't really see why I can't just follow suit here. The most important thing to me, though, really is that I end up with the right answer. And I believe this is the same thing. I agree. And I agree. Okay, so in the next few problems, figure out the limits at negative and positive infinity, and then write down the equations of any horizontal asymptotes for the function. Okay. So by horizontal asymptote, they mean essentially an output that it would never give, an output that it would never give. Whereas a vertical asymptote would be an input that it can't take, an input that it can't take. So I say that the limit as x approaches negative infinity of f of x in this case, we just really need to pay attention to the negative 4x squared over 9x squared terms, as these other two will become irrelevant. In which case, it would be negative 4 over 9. And likewise for the limit as x approaches positive infinity. The squaring renders the sign irrelevant. As for an output that it would never give, an output that it would never give, how am I supposed to think about that? I guess it would never give negative 4 over 9. So would I just simply say this is my horizontal asymptote? Not sure. We'll have to see. Okay, so I suppose I could sort of play ball here and imitate what is happening in these arguments. We know that there will be a horizontal asymptote for x approaching negative infinity. The limit of x approaching negative infinity of f of x exists and is a finite number. Okay, I think I understand now. Yes, I understand this now. Okay, so let's begin. Let's consider question 4 then. So, to imitate the arguments that he had, the limit as x approaches well, I'll just start with infinity. As x approaches infinity of f of x would be the same as the limit as x approaches infinity of, let's see here, what can I do here? Not quite. Well, maybe. Yeah, so I'm imitating what was said. So it won't be a finite number. It won't be a finite number because I've got a 7th degree polynomial divided by a 2nd degree. So it'll behave like a 5th degree. And so it'll shoot off to infinity. So I'm going to be extremely surprised if I get a constant number back. Okay, so we go down here and we check. Yeah, exactly as I thought. And because both of these limits are infinite, it won't have a horizontal asymptote, right? Or will it? No, it won't, based on the reasoning from earlier. But anyway, I guess I have to think about what it will actually tend to, and it will go to negative infinity. Is positive infinity. Okay, so 1/4 degree polynomial divided by another. And, I can just straight away see that the limit is going to be 4. Here we have a cubic over a quintic, a third degree polynomial over a fifth degree polynomial. And so it's behaving like 1 over a quadratic. But I guess we have to make it more rigorous, so to speak. Yeah, we're in agreement. Okay about that. All right, so in the sixth one, I'll be more rigorous about it. The limit as x approaches infinity of f of x. Sorry, the sixth one, if I misspoke. So we factor out x cubed, and we obtain 1 minus 2 over x squared plus 11 over x cubed. And on the denominator, we can factor out x to the 5, and we obtain minus 6 plus 3 over x to the 5. And right, what would be more efficient here is to just declare that f of x is that, and then to say that pretty much declare that it's equivalent. So the limit as x approaches infinity of this will be 0. And the limit as x approaches negative infinity will be 0. But what about horizontal asymptotes? Zero then. Or so I think. Yes. All right, in the seventh problem. I know where this is going. It's a seventh. And the eighth. If you're taking this, I mean, this 7 is completely irrelevant, but you're taking the square root of this, so it'll end up behaving more and more like 3x for larger values of infinity. And so we have negative 3 over 2. Whereas for negative infinity, it's going to be 3 over 2. So no vertical asymptote because they do not agree on the sign. That's what I believe. Or we're about to see if that's true. Oh, that's for negative infinity, of course. So they go through all this business of factoring out x squared, then using their fact that will tend to 0, their quote-unquote fact, which they haven't proven. And then, good, this actually will be the absolute value. And then they factor out x from there, and so on. Oh, okay, so we get 2. We actually get 2 vertical asymptotes. And the 9th one. So this will start behaving more and more like root 2x. 1 over root 2 then. And the limit as x approaches negative infinity of f of x. Same considerations, but negative 1 over root 2. And these will become the horizontal asymptotes. Problem 10. And it can't come soon enough for this type of work, for this particular type of work. Okay, so the denominator behaves like root 7 times x squared. And then we have negative 4 over root 7. In fact, that's true regardless of the case. And that becomes the horizontal asymptote. I need to remember that. These arguments, they're really flimsy. Do you know what it is? It's sort of like, it's like half analysis, you know, and that's why I'm not really indulging them so much. You get a few facts, and then you have to do this long, drawn-out factorizing of these terms, and it's just, I just find it to be rubbish. Sorry. I know that he put a lot of effort into writing them, but I just don't find these very engaging. Cool. Like, a lot of people, they're just giving them information, and that's fine, because people just need to get a move on, you know, and apply it to real world problems and understand these pieces of technology. But I just don't like it when it's what a limit is, and, you know, here are just some facts, just pretend that you're doing analysis, and it's not that great. Okay, so I'll quickly look at this, and then hopefully we can move on to continuity. Yeah, I'm not going to provide like an extensive argument about this. Really, all I just want is just confirmation that I can actually find the limit in the end, because the arguments that we're supposed to do are rubbish. Sorry, they just are. So I'm going to make a table, and I'm going to say the limit as x approaches infinity of f of x on the left hand side, and then I'm going to say the limit as f of x approaches negative infinity on the right hand side. For function 1, as x approaches infinity, what happens to this guy? The answer is that it shoots off to negative e to the negative infinity, which is 0. And if I put in negative infinity, well, I have to cube it, and then I get e to the positive infinity, which is infinity. For problem 2, put infinity into there. Okay, so the whole thing behaves like 2x. The whole thing behaves like 2x at infinity. And then what's e to the 2 infinity? Well, it's infinity. Again, the whole thing behaves like 2x. And what's e to the negative 2 infinity? 0. And here, okay, at infinity, who overpowers all the others? The first term. And for negative infinity, these turn to nothing, and this one turns to well, I guess nothing as well. So we end up with nothing, minus nothing, minus nothing, so nothing. So I think those tend to the first three, however minimally they do. Okay, we agree, we agree. We agree, we agree. Ooh, uh-oh, whoa. Hold on, just a minute now. Oh, darn it. I'm supposed to put negative infinity up there, and then times that. Oh, darn it, a sign slip. Like that. That's correction. Okay, great. Now we can do the next three. Okay, in the fourth one, what do we have? Okay, I have 0, minus 0, minus infinity. So it'll be minus infinity. And here, 3 to that, that'll be 3 to the infinity, which is infinity. And then here, negative 5 times negative infinity and positive infinity. So infinity, I guess, or 0. So we have to contend with this infinity minus infinity business. So what do we do? Well, we have to think of it. So what we're going to do is we're going to factor out e to the x. It doesn't work like that. How does one do this again? I want them all to be positive, right? Okay, I just need to remind myself what's actually going on here. Like that, right? How can I use this? Okay. You know what? This is good. I'm actually happy about this. I wanted to get speed through these problems, And now I've met one that's actually kind of cool. So we're just going to pretend that we have this to deal with, because for some reason it's just not coming to me right now. So if I were to factor out e to the 10x, then that would turn into a 1, of course. And what would happen to this? Well, I have to do e to the minus 5x divided by e to the 10x. And so minus 5x minus 10x, so minus 15x. And then e to the minus x divided by e to the 10x, so e to the minus x minus. So you'd get this. And, oh, darn it, this doesn't work. Well, all right, look. Look. That goes to 0. No. E to the minus infinity, that goes to 0. And that's going to go to 0 as well. It's this one. Oh no, that's the very trouble that I'm trying to contend with. Minus infinity. Okay. So it's only the first two terms that I actually have to care about. Right? It's only the first two terms that I actually have to care about. And the 3 and the 8, they just don't matter. The question is, what happens to this as I put in, like, negative infinity? As e tends towards negative infinity, I suppose you formally say. That would turn into infinity, and that would turn into infinity. And this is like a big problem. A big problem. So can I make any progress? I cannot see how. I cannot see how. So what you do is you just factor out e to the minus 5x. Because what will this turn into? Minus x minus 5x. So e to the 4x. And what will this turn into? It should just turn into 1. And so that turns into 0. And that will turn into constant. And so I think I get it now. I really do. All right. What do I make of this fifth one here? Okay. All right, so on the numerator, as I put in x equals infinity, I will get negative infinity. On the denominator, as I put in x equals infinity, I will get positive infinity. So I need to be careful now. So I think it'll approach a constant. So what am I going to do? What I'm going to do is I think it'll just be negative 2 over 9. I think it'll just be negative 2 over 9. And for negative infinity, okay, what happens? That very first term there shoots off to infinity. That one there is 0, so I'm going to have infinity on the top. And then here, that will disappear. Negative 3 times negative infinity. Well, that would be 3 infinity. So I'll get negative 1 over 7, I think. Let's see. Let's see. Okay. Right, we agree. Now we agree. Great. Problem 6. Okay, I'll have to think. For negative, no. What am I going to go with first? Just do infinity first. All right. That'll disappear. That'll become this. And so will that. And down here, we get this. Right, okay, so I have to be delicate with that. So I'll ignore that first term now, which just completely turns irrelevant. And then for these two here, what I will do is factor out e to the x. Okay, so let me just make this totally clear in my mind. That and that become irrelevant, and it's only that I have to care about. So it's going to behave like this. Yeah. And then let's think about this now. That guy there is going to overpower those ones up there, isn't it? For ever higher infinity. And so I end up with that, which is 0. Okay, so I think it's 0. Now, what do I do for negative infinity. Okay, so first term behaves like that. Second term disappears. That term disappears. This behaves like this. This disappears. And this behaves like this, doesn't it? And what do I think? I think this overpowers the two underneath. And I think it's going to be infinity. I think it will be infinity. Yeah. All right, so let's check. Okay, we agree. And we agree. Okay, great. All right, so now these problems. The natural logarithm as t tends to negative infinity. So it ends up being infinity in there. And what's the natural logarithm of infinity? Well, it's saying to what power must I raise e in order to get infinity? And the answer is infinity. For this one, okay, so that whole thing will start to behave like 3z squared. And then if I do 3 times the square of negative infinity, I get 3 infinity. And so I think it'll be infinity as well. Better check those two. Mm-hmm. All right. Here, this whole thing will behave like 1 over x squared. And so like 1 over infinity, so like 0. So ln of 0 is what? What power must e be raised in order to get 0? Negative infinity. So this will be like negative infinity and arctangent of negative infinity. Well, depends on the agreed upon range, agreed upon domain, doesn't it? So I would say negative pi over 2, but I may be wrong. I really hope they don't sort of pin down the domain of arc of inverse tan in that way, but if they do, so be it. All right, awesome. Problem 11. Okay, this whole thing will behave like negative infinity, won't it? No, it won't. No, that's wrong. It'll behave like negative 7. And what's the arctan of negative 7? Okay. All right, so that'll tend to 9w, and it'll tend to infinity. And arctan of infinity is pi over 2. Yeah. Okay, great. So I didn't want to continue the limits at infinity section for too long. All right, so this will be kind of cool. Right, let's title it and let's get going. Based on this graph, determine where the function is discontinuous. -4 and 2 and 4. Where is it discontinuous? -8, -2, and 6. All right, that's good. These next problems use the limit properties and the definition of continuity to determine if the function is continuous or discontinuous at the indicated points. All right, so time to do the work. We'll pause here, actually. We'll pause here. Be well.